Welcome everyone, and for this new MLIR meeting, today we have Tal and Berke who are here to present about their work on data-centric modeling using MLIR.
Okay, hi. So we will present this in two parts. So basically, I will start with giving a brief introduction to DaCe, which is a data-centric framework, and an intermediate presentation of code. And then Berke will talk about the MLIR aspect and how the dialect works with the MLIR ecosystem. So the story behind the data-centric framework starts around 2017. So this is something that we've been developing for a while now. There are a lot of people involved. So as you can see, there's quite a bit of a list here at the top, but there are more people that I'm obviously forgetting. And this is something that we've started, in parallel with actually a bit before MLIR, and as MLIR kind of appeared and rose, this is an excellent opportunity for us to kind of combine the strengths of each basically infrastructure. So the story behind DaCe is a story of separation of concerns. If you look at today's hardware architecture landscape, there are plenty of architectures, and currently the performance is mainly dominated by data movement. And as you can see here in a small example that I wrote in Python, of course, you can always write it smaller. If you were to execute this matrix multiplication on a, let's say, Python interpreter as is, obviously this won't run fast. But as a performance engineer, if you optimize it to a certain hardware architecture, for example, to tensor cores, then, well, this short code that represents a matrix multiplication suddenly becomes very, very long. So this is just a code sample from NVIDIA, and already it takes 300 lines of code. But the interesting thing here is that while the operation of a matrix multiplication, the core operations, computations have remained the same, the data movement is what is different. And so if we go even further to more optimized implementations, of course, this goes beyond 300 lines of code. And again, it's telling the same story. So even the highest optimized versions of a matrix multiplication are just, let's say, mutations on how the data moves and nothing about how the computation is actually performed. So these are basically the two kind of insights that we see here. And in today's world, basically, high performance optimization means reduction of data movement. So with that in mind, we designed a representation that allows data movement optimization without modifying the original code. And since we're dealing with separation of concerns, first of all, what we want to do is to make this intermediate representation explicit in the middle and as a specific role of performance engineer. Because while compilers might be able to do the job automatically well for the most part, there will always be someone, when you optimize, especially performance critical applications, that will have to go and tinker with the code. So a domain scientist, or let's say a front-end user, might write their applications in a wide variety of languages. I'll get to that in a bit. Then we lower this higher level algorithmic representation into a data-centric program, which is represented by an intermediate representation called the Stateful DataFlow multigraph, or SDFG for short. This representation then can be modified without touching the original code through graph rewriting transformations. And then we can take that transform into DataFlow and run it on a wide variety of architectures, CPUs, GPUs, FPGAs, and even clusters thereof. But as I said before, since we're dealing with separation of concerns, the main idea behind the DaCe framework was to create an ecosystem around this IR, this SDFG, and essentially create feedback loops into the language itself, which means instrumenting and visualizing the graph and allowing to write and extend transformations very easily as an end user. So let's start with, what does it mean to be data-centric? I mean, I mentioned this once or twice, but I haven't really defined it. So there are 4 principles to data-centric programming. And in essence, it's kind of provided as an alternative to starting from procedural or imperative languages and going to introduce or to incorporate data flow into them, which is something that we're seeing in compiler infrastructures today. but more to go the other way around, to start from data flow itself and introduce control flow concepts into that. So first and foremost, it means that we separate explicitly data containers from the computation. And the idea that data movement exists as part of the language, that basically it's a first-class citizen in a data-centric representation. And as opposed to, let's say, more traditional representations, the data is first, the execution is first governed by data dependencies. And so if you have something that has no data dependencies, it can execute in parallel. And we introduce control dependencies only when the data flow is not implied or when it is necessary, basically. So in a data-centric representation, there is basically a different view on things, right? So in a sense, in a control-centric world, coarsening would mean, or a multi-level view would mean, like, for example, procedures or dialect calls that would have their own implementations within them. But in a data-centric view, coarsening means essentially that you have a segment of the code that requires a subset of an array. That's just one of the examples. And so we want to allow in our representation a multi-level view of data movement throughout the entire application to allow for local optimizations, but also global optimizations. And to do that, we designed a representation. So representation is graph-based. For some of you who are familiar, I mean, this goes back to the late 70s and the definition of data flow graphs, but then tries to address the problems that data flow or pure data flow representations have. So let's take this computation here, x squared plus n of x over pi, and let's put it in a box. In order to compute this, of course, we need x to come from somewhere, y to go somewhere else. So we denote the memory locations in circular nodes, and the octagonal nodes here are computations. And in all of our transformation infrastructure and optimizations, we actually do not look at the contents of these computations. And we just call them tasklets, and we only mutate data movement around them. The data movement units, those edges here, we call memlets. And of course, the names kind of are familiar for you, then it's really interesting, but also kind of coincidental. So we can name these memory regions and now express parallelism natively. You know, if you have A at 0 going to one tasklet, A at 1 going to another, then they can run completely in parallel. But now there is a problem that occurs pretty often with with the data flow representations, is that the sizes can be prohibitively large, right? For example, 200 by 200 matrix multiplication, or even symbolic in size. So we don't even know what n here is, but we still want to optimize it all the same. So what we do here is, since this is a parametric graph, we want to represent it as such. And so we use the fact that a lot of the computations today are actually following, repeating subunits. And so we can group them together and construct what we call a map. So a map is a scope. The scope is defined by the subgraph dominated and post dominated by these two nodes respectively. And we say that this scope is replicated for the number of times defined by this set here, integer set. So the nice thing about the DaCe framework is that the representation here contains a lot of symbolic expressions. So everything here is completely parametric, A at I, B at I, and you don't need to specify everything. So in a front end, we only need to take this internal part, and we use a symbolic math engine to propagate this set with this set in order to get the outer set. So if you are accessing, I don't know, one column of a matrix, we know only to copy that column to a GPU. Now, as opposed to other representations as well, another problem that we have with data flow programming is that if we have two components side by side here and no data dependencies between them, as I said, sometimes we cannot just imply data flow through, imply order through data flow, and this would create a data race. So what we do is, similar to existing representations, we wrap these acyclic multigraphs of data flow with a state machine, which is a directed graph, and that has a different kind of edge. So these blue edges can have assignments or conditions, and then you can concisely represent stateful applications as well. And so with that, we kind of represent stateful data flow, right? And the goal here, as opposed to the other representations, is to try to make the data flow segments, the states, as large as possible. Sometimes we have applications that have, like, say, 30,000 lines of code, and they would have the order of tens of states. And that's the entire idea. And So all in all, this language doesn't have too many elements because basically our computations are enclosed within this tasklet, right? So we have the states, we have tasklets, we have data containers and the maps that you've seen already. We also have, if you need to nest control flow within DataFlow, we can, under certain conditions, if DataFlow is acyclic around it, we can create a nested SDFG. And we have containers that behave more like FIFO queues. So there are streams, and there's the producer-consumer, let's say, map counterpart of a stream. If we are writing to the same memory location from multiple places at the same time, we can define a conflict resolution. And lastly, if we want to do some data, like domain-specific optimizations, we can define nodes that are like library nodes, exactly like dialects are, basically. And we have full operational semantics for this language if you're interested in the original paper. But of course, I mean, I've been talking about this, and again, I've been reiterating that this all may seem very familiar, right? So as a kind of a parallel effort to MLIR, we see here a lot of similarities. I mean, except for the graph part, right? You know, the scopes can be represented by a fine parallel, for example, and so on. And this got us thinking, you know, I mean, why are we not a dialect here? So Berke, of course, will talk about, you know, how this was exactly implemented. But what I do want to go over is a bit of a differences between MLIR and SDFGs. So first of all, as I mentioned before, we have a parametric data flow graph. So we use symbols quite a bit. And we kind of differentiate symbolic expressions from identifiers. So in an SDFG, for example, this is, let's say, code written in Python. We use symbolic expressions with named symbols to represent sizes of data containers. So we don't have a question mark, for example. We use that for type and shape inference, and we also use that to check for out of bounds accesses. So for example, here, a plus b is not going to work, and we're going to fail that as we create the graph. In MLIR, you know, I mean, if you had an operation called linag add, you can represent it with linag.generic. This, of course, cannot be verified directly if you have a question mark. So the idea here is to keep this sort of correspondence between multiple data containers. And so that's difference number one. And I won't get into it, but there are certain definitions of what can be a symbol, and we can promote certain scalars to symbols. Another difference is what I said about tasklets before, so that they're not really a basic block. They could do anything in any granularity in a tasklet. For example, this Mandelbrot set computation, as long as they don't access anything else on the outside. So they have to have the data fed and read from them, but they can do anything. So for those kind of optimizations, we use directly the compilers. All right, so another difference is more a difference between LLV MIR and SDFGs. So essentially how we represent our control flow graph. So as I mentioned before, we have a state machine where we can annotate assignments and conditions here, and that represents our program. And that is as opposed to what you would see in a CFG in LLV MIR, where you have only the true and false and basically the branches, which could stem from any kind of computation, be it some symbolic expression or a data-dependent expression. And so while the two representations are commutable, right, we can think of any SDFG as MLIR and almost any MLIR as SDFG, it is important for us to have this information readily available to us for some of the transformations to understand, for example, if a data dependency is governing some of our executions, and we do that for modeling and for other purposes. Another difference is just the way we annotate memlets. We have them everywhere, so we can nest maps in each other here, and you always have some form of expression on any of the intermediate data movement units. So we can use that to very easily construct, for example, local storage in between, or create copies. And we can always trace them to concrete memory locations. So there is always some path that goes from a data container, and we know always which one it is. So less chances of aliasing. Not that there is no chance for aliasing, but there is less of a chance. Another thing that we do is memory allocation is another data container that we have here. So what we call those are our transient containers. And so in the sense that control-centric representation can do that code elimination, we can see segments of memory that is not going to be used. For example, here we only access the second half of the IF column of A, And we can do dead memory elimination, for example, to reduce the allocation size. And we can do these kind of global analyses for as much as we know that things may not alias with other things. And with transients, that is definitely the case. And so, yeah, from here on out, I mean, I will just go over the few things that we were supporting in the DaCe ecosystem around the SDFGs. We support Python code, right? So as input, so we support just-in-time computation with all the object-oriented programming and basically fed objects. We also support ahead-of-time computation with the type hints. We support PyTorch, just add an annotation on top of a neural network module, and we can compile that. I'll show some results in a bit. And we even support C code, just native C, not C++. And yeah, I mean, this is very limited, and all the front ends are kind of similar. And of course, a front end or interaction with MLIR would be very useful here. Now, let's just a little bit talk about the transformations and how we use this to map very efficiently into hardware. So what I didn't mention before is that these maps, these parallel scopes, they have a schedule attached to them. So this is basically something that is user-extensible but defined by a certain type. So for example, if you're CPU multi-core or single core, they represent different codes that could be implemented. Same goes for the containers. They can have their own storage locations. And this basically maps to code directly. Now, if I wanted, instead of running on just a single core with simple C code, if I wanted to run on ARM SVE, for example, the scalable vector extensions, all I have to do is change the schedule here to SVE, and then the code that is generated is completely different, but structurally similar. Similarly, if I want to go into GPUs, what would normally take a whole code rewrite, in this case is just 200 lines of Python code of a transformation, like a simple graph rewrite, that adds intermediate storages set on the GPU and change the schedules of these maps, and now we have kernels. Right, so in that sense, it's very easy to represent heterogeneity and parallelism and optimizations. And all of that, of course, without ever changing the tasklet code, that remains the same. Now, transformations can do a bit more than just changing the target. We can, for example, see here that if we write a matrix multiplication where we store everything to a large three-dimensional buffer, this is obviously wasteful, but since this is a transient array, we can look at this whole subgraph and do a simple graph rewriting transformation that would replace it with a more classical version of a matrix multiplication. And so, these kind of transformations are obviously similar to you, and we run, the exact same techniques as all other compilers. And what we also do is we allow people to change and edit the graphs, view them, inspect them, and even transform them directly within Visual Studio Code. So as I said before, that part of this process is to create a feedback loop that allows people to transform, rerun, and keep optimizing the code, again, without touching the original source code. If you don't know which transformation to run, we even provide some instrumentation tools and modeling, such that when you feed the values of the symbols here on the left-hand side, you can even get some flop analysis and data movement analysis, and so forth. And yeah, all of that. And this is essentially all the tools that we have, that and some API to run transformations. And with that, we can map the code to a wide variety of hardware architectures, talking about Intel CPU, Power 9, and SVE, and ARM, NVIDIA and AMD GPUs, Intel and Xilinx FPGAs. So it's the same representation, but now working with FPGAs as well, right? So directly, we have also sets of transformations that can create streaming compositions of applications to turn them into FIFO, and that works, or that maps very well to circuitry. And when we work with clusters, we work with MPI. And all of that, again, in the data-centric concept, it's just data movement across different storages and running code in different schedules, essentially. So in terms of performance, I'll just get a brief overview. So just trying this automatic optimization heuristics that we have with DaCe running on Python code. So if we try NumPy bench, which is a benchmark of 52 scientific applications written in Python for different domains, we can see that DaCe provides a really nice speedup for CPUs over NumPy and Python. If we talk about FPGAs and GPUs and even distributed architectures, we see the similar things where it can outperform pretty much any other general framework that would run these applications. If these simple scientific benchmarks are not enough, we also do graph analytics. So for example, fastest breadth-first search on GPUs. And in this C front-end, we took the entire Polybench benchmark set and we just converted it, and also can get a competing performance with the polyhedral compilers, even though we are not polyhedral in the sense we have general sets and nothing specific that relies on polyhedral analysis. If that is still not convincing, we can grow a bit bigger. So with the same C front-end, we read full unstructured hydrodynamic simulation and can beat the original code's parallelized performance. So we took that, removed all the OpenMP annotations, and we got some code that ran faster than what the parallel version of the original authors were. If you're interested in deep learning, we, as I said, with the PyTorch frontend, we're able to outperform compilers like XLA, so JAX and TensorFlow with XLA, as well as TorchShit by interesting factors for a wide variety of neural networks. Also for numerical weather prediction, we can optimize single stencils for CPUs, GPUs, and FPGAs, but we also convert an entire weather model into one of these graphs. This is the 30,000 lines of code that I mentioned. It's 30,000 lines of Python that we just parse into this graph and run some global optimizations and can achieve performance that is higher than other GPU implementations. And lastly, we also ran a quantum transport simulation, which was kind of interesting to see because the data movement transformations that we were running were very coarse-grained. We changed the entire communication infrastructure by changing the way we distributed the maps. So it's same concept, same language, same graph, but then we were able to outperform the previous implementation by a factor of 140, running on a full supercomputer, 27,360 GPUs, and achieving over almost 60% of the entire cluster. And for that, we won an award, the Gordon Bell Prize in 2019. So that would be it for me. And now I will pass the torch along to Berke to talk about the more specific efforts in MLIR.
Thank you, Tal. I'll just share my screen. So can you see the slides?
Yes.
Okay. So welcome to the second part of this talk.
There were a few questions online. I don't know if Berke, you wanted to take there were a few questions while you were presenting, or Tal, sorry.
I will try to type the answers in the meantime, if it's okay. Or
yeah, in the meantime, you said so now, right? Yeah. Okay. So yes. Someone was asking about how you model stateful, or if stateful was part of the model, because you were initially showing it as a pure kind of computation.
Yeah, so this is quite interesting, and Berke will talk exactly about some of that soon. So what we start with when we read in the front end is a very, very stateful representation, so states per statement, and then we run simplification transformation. So basically to coarsen the control flow and fuse those together if they follow certain conditions. For matrix multiplication, we were able to outperform kublas several times, especially in the quantum transport simulation by a factor of 5. And we were able to reach 98.6% of MKL with as few as something like 7 transformations on the original code. So if someone asked about matrix multiplications, it's actually quite an interesting application. Yes?
There was a question at the end as well about Polybench, and if you have insight into what optimizations in your framework in particular give better optimization compared to us.
So some of the things that we do, so we ran in a completely, let's say, not tangential, but completely separate approach for auto-parallelization than the other approaches that were currently out there, for example, in the polyhedral tools. And so sometimes we were able to represent more parallel sections automatically, but not always. So in some applications, if you look at the example, I will send links to all the papers. If you look at the examples, in some of them we are ranked first, but some of them were not. So of course there are other transformations that we have not yet implemented, but I would say that this is one of the main concerns. And the other one is that we can look at memory allocation, right? So when we looked at Polybench, we actually took the entire code. So we saw temporary arrays as transients. We were able to eliminate them in some of the cases. I think there were, especially in the stencils, FDTD, 2D, ADI, I think, not sure. We were able to run transformations that were not possible if you don't know that things could be removed, right? So that was another source of our speedups. And DaCe papers, I'll just send the links if that's okay on the chat.
Awesome. Thank you very much. All right, Berke, for the second part.
So welcome to the second part of this talk about the data-centric dialect called SDIR. In this presentation, we will first look at the motivation, then our MLIR dialect called SDIR, after which we will evaluate our dialect, and lastly summarize this presentation. Our goal with this project was to connect MLIR with DaCe by creating a high-level dialect called SDIR. SDIR stands for Stateful DataFlow IR and aims to provide a data-centric dialect. By implementing a translation from SDFGs to SDIR and converting SDIR to a core dialect, we can allow DaCe to compile to all targets supported by MLIR. By going the opposite direction, which means converting from a core dialect to SDIR and translating SDIR to SDFG, we can generate SDFGs from languages supported by MLIR, and therefore use DaCe for optimization. By combining both of these ideas, we can enable DaCe to be included in any optimization pipeline in MLIR. Now we will look at the SDIR dialect. States, as we have seen before, are represented by the state operation. The state operation has an attached symbol. In this case, the symbol is state 0. This allows us to reference the state later on. We additionally attach the region, which represents the body of the state. Access nodes are represented by the getAccess operation. In order to use the getAccess operation, we first need to allocate the arrays. This can be seen in the first two lines. In the last line, we can see a copy operation copying from A to C. For the copy operation, we use the custom parser in order to allow for this arrow notation, which clearly shows the movement of data from A to C. Now, tasklets are represented by the tasklet operation. Similar to the state operation, we attach a symbol, in this case the symbol add, to reference the tasklet later on. This symbol is followed by the argument names and the return types. In order to name the return values, we added an attribute called outputs, which states the output names in the order they are returned. In the attached region, we write the code contained in the body of the tasklet. Other dialects may be used in the attached region, which means that variables can get renamed, since we have no control over other dialects. In this example, we can see that the variables C and D got renamed to R0 and R1. This is why we need an attribute describing the output connector names. We can derive the input connector names from the arguments of the tasklet. Since we have control over our own operation, we can disable variable renaming. If we try the same with the return operation, we can see that due to variable renaming, the connector names are lost. The attribute allows us to derive the correct connector names regardless. Let's look at a simple example combining the concepts seen so far. As we can see in this example, we first define the state, and in the body of the state, we start by defining the tasklet. After that, we create the access nodes, and lastly, describe the movement of data by loading from A and B, calling the tasklet, and lastly, storing the result in C. Map scopes are represented by the map operation, which uses a custom parser. It starts with the variable name used inside the scope. This is followed by the lower and upper bounds, and lastly, the step size. In this example, we can also see how we represent symbols. In order to use a symbol, we first need to allocate it using the alloc symbol operation, which takes a string representing the name of the symbol. By using the keyword sim, we can describe symbolic expressions and use them instead of integer constants. Consume scopes are similar. They have an attribute called NumPy, which represents the number of processing elements, and a second attribute called condition, which defines the stopping condition. This is followed by a stream and the variable names for the processing ID and the popped element. In this example, we can also see how we represent write conflict resolutions. In the last line, there's a store operation with an attribute called WCR, which represents the write conflict resolution we would like to use. SDFGs are represented by the SDFG operation. The SDFG operation has an attribute called entry, which references the entry state. There's a region attached to the SDFG operation containing the nested states and edges. The edge operation has two optional attributes called assign and condition, which describe the assignments and conditions of the edges accordingly. We again use the custom parser in order to allow for this arrow notation, which clearly shows the movement from one state to another. As we have seen before, symbols can be allocated with the alloc symbol operation, which takes a string defining the name of the symbol. In order to access the symbol, we call the sim operation, which returns the value of the symbol. We can also use the sim operation to execute symbolic expressions, as we can see here. And symbols can also be used as parameters for types. So as we can see here, we use the sim keyword in the memlet type in order to set the size to the value of the symbol k. Lastly, symbols are used in edges to assign values to them or in order to define conditional edges, as we have seen before. Now let's look at the translation process. Similar to all the present MLIR translators, we don't directly write to a stream while translating an operation. Instead, we implemented a JSON emitter, which restricts the output to a valid JSON, because SDFGs are stored as JSON files. The JSON emitter helps with debugging and reduces errors, because it takes care of the braces, brackets, and commas, and also indents the output automatically. The JSON emitter also simplifies the translator, as we will see in the next slide. In this example, we can see a getAccess operation and the function that translates it to its SDFG. As we can see, the JSON emitter helps us to focus on the content of the JSON. Furthermore, we can see that the code also closely resembles the resulting JSON. This becomes even more apparent if we start indenting our code in the same way as the JSON. Of course, from a C++ point of view, this is improper indentation and is therefore not used in the actual project. By default, the JSON emitter will print every value as a string. In some cases, we need to print literals, such as integers, booleans, or nulls. We can see that we achieve this by providing a fur argument, which disables the stringification. We added translation functions in this fashion for all the operations in SDIR. The translation functions only emit non-default entries, as DaCe fills in the default values upon loading the SDFG. For operations that contain a nested region, such as the SDFG operation, we traverse all the operations in the region and call their appropriate translation function. This leads to a mutually recursive translation and ensures that we traverse all operations. In this example, we go through all the states inside the SDFG operation and translate them by calling the translate state to SDFG function. If any of the states fail to translate, we abort the translation and report a failure. In the current MLIR specification, there's an implicit top-level module operation. We use this implicit module operation in our translator as the entry point for the recursion. We additionally added a lifting to Python for short tasklets. By short, we mean tasklets consisting of two lines, such as binary operations or constants, as we can see in this example. Although DaCe supports tasklets written in MLIR, it performs far better with tasklets written in Python. This lifting leads to considerable performance gains, since short tasklets like these can occur often. Before translating, we rewrite the IR in order to ensure a correct translation. In this example, we can see that the call operation accesses the first argument without allocating it. In order to mitigate this issue, we insert allocation operations for each argument. After that, we insert access and load operations and rewrite all operands to the result of the load operation. Another pass we perform is the elimination of dead load operations. In this example, we can see that the last load operation isn't used. So there's no point in translating this operation, and therefore we can safely delete it. Lastly, we also insert access operations for stores. If we look at this example, it seems rather harmless. We first get access to an array, load the value at the index, call a tasklet, and store the result in the first entry of the array. However, if we look at the produced SDFG, we can see that this generates improper data flow as it causes a cycle in the graph. In order to mitigate this issue, we add a second access operation and rewrite the store to use this access operation. If we look at the data flow graph now, we can see that it's exactly what we expect and everything is in order. Additionally, we also implemented a converter that converts the Arif, memref, and SCF dialect to the SDIR dialect. We chose those three specifically because Polygeist primarily emits those three dialects. Our plan was to use Polygeist with our converter in order to get SDFGs from C code, which creates a new optimization pipeline for C and also eases performance of evaluations. Now let's look at how the converter works. First off, we convert func operations by replacing them with an SDFG operation. As you can see, we take over the body and the parameters of the func operation. Additionally, we insert an init state and add it to the entry attribute of the enclosing SDFG operation. For the arithmetic operations, we wrap them into tasklets first. As you can see here, we also change the operands to the arguments of the tasklet and add a return statement for the result of the operation. We then proceed by allocating a transient array in order to store the result of the tasklet. After this, we enclose the tasklet with a state. As you can see here, in the state, we inserted multiple operations. The first operation calls our tasklet, which is followed by getting access to the array and storing the result. Lastly, we add an additional load operation. We will see the point of this load operation in the next slides. In this example, we can see how the multiplication operation depends on the result of the addition operation. In order to resolve this, we change the value to the new load operation. Of course, this IR is illegal because we're accessing a value defined inside another region. We will resolve this when we convert the multiplication operation. After this, we add an edge linking our state with the state right before it. This is why we inserted the init state in order to ensure that the previous state always exists. And lastly, we erase the addition operation and continue to convert the multiplication operation. We convert the multiplication operation in the exact same way as before, but additionally, we check for operands that are defined by loads. In this example, we notice that the second operand is defined by the load operation of another state. We follow the operand of the load operation in order to get to the allocated transient array. In this case, we found that the array called temp2, and we access it by inserting a getAccess and load operation. Notice how we didn't rewrite the first argument because it is defined by the enclosing SDFG. We proceed by inserting an edge again, linking to the last defined state, and erasing the operation. We continue to do this conversion with every operation. MemRef load operations follow the same scheme, but they don't generate a tasklet as we have a load operation in the SDIR dialect. Here we can again see how the operands get rewritten to access the result of another operation and how the arguments stay the same. Lastly, we again create an array and store the result in it as we have done for the arithmetic operations. Notice that we also convert the memref types to the SDIR types. Question marks are replaced by symbols, which we mark with the sim keyword. The memref store operation is even simpler. It works the same way as we have seen before, but here there's no need to allocate an extra array as the store operation has no result. We therefore omit the operations for those. Now let's look at SCF for loops. A for loop expands to multiple states. We move all operations nested inside the loop out of the body. We will look at how we rewrite the iteration variable later on. On the right side, we can see a depiction of the generated states. The init state connects to the last state that was defined as we have seen multiple times. After that, we connect the init state with the guard, which is responsible for checking the loop condition. We add two special edges to the guard, one that conditionally connects to the exit state if the condition is false, and one that connects it to the body state otherwise. Now, as you can see, all the operations in the loop body come after the body state, which means they will all connect to the body state, forming a chain of states. We then connect the last operation to the return state, and lastly connect the return state with the guard. Again, we use a special edge to increase the loop iteration variable. And of course, all operations after the loop will connect to the exit state as it occurs at the end. With the conversions we have shown so far, the last operation wouldn't connect to the return state, as we always only connect to the previous state. In order to solve this, we mark the last operation in the loop body to link to the next state. We do this by inserting an attribute called link to next. All the conversion patterns we have seen so far also check if this attribute is set, and if so, in addition to connecting to the last state, also connect to the next one. This way we can ensure that the loop is properly connected. We represent the loop iteration variable by a symbol, which is why we need so many states. As you can guess, the init state initializes the symbol to the lower bound. The guard state checks the symbol for the upper bound and goes into the body or exits accordingly. And lastly, the loop return state increases the symbol by the step size. We additionally insert a sim operation which accesses the symbol. All the operands which were using the iteration value get remapped to the symbol. This concludes the converter, and now we'll look at how we evaluated this dialect. To evaluate SDIR, we chose 5 polybench benchmarks, namely 2mm, ADI, Gemver, Heat 3D, and triangular matrix multiplication. We ran them on the CSCS alt server, the specifications of which are shown on the right side. We built a compilation pipeline for SDIR, which we will look at in the next slide. We then compared SDIR with Clang, GCC, Poly, and Pluto. And additionally, we ran the benchmarks single and multi-threaded to compare the performances. We ran these benchmarks 100 times on a large dataset defined by Polybench with 10 runs of warm-up. In our compilation pipeline, we first used polyguys to get MLIR code from the C benchmarks. After that, we used the script to extract the kernel function. As mentioned before, polyguys primarily emits the Arithmetic, MemRef, and SCF dialect, which is why we can use our converter to convert the kernel to SDIR. We then translate the SDIR to SDFG, and lastly, optimize and compile with DaCe to get an executable. We also wanted to run benchmarks using optimizations in the affine dialect. Here you can see the optimization pipeline we used. In this pipeline, we primarily optimize loops, after which we lower through multiple dialects, and lastly compile with LLC and Clang. Looking at the plot for the 2mm benchmark, it's clear that both affine versions are running sequentially. We tried to use the OpenMP dialect to use multiple threads. However, because it's still in development, we couldn't incorporate it into our pipeline as it produced output that was invalid. So we didn't perform these evaluations, and instead we compared the benchmark with Pluto and Poly. Here are the preliminary results for the parallel benchmarks. In most cases, we are on par with either Pluto or Poly, and in 2 benchmarks, we even outperformed them. Particularly interesting are the results for the ADI benchmark. Pluto had a compilation error in this benchmark, which is why there are no measurements. Initially, DaCe didn't detect parallelism because of the symbols and the memory sizes, so it was run sequentially and was far slower than Poly. After writing an optimization pass that mitigated this issue, we can see that SDIR runs 4 times faster than Poly on the ADI benchmark. Looking at all the results, however, we noticed that Poly doesn't seem to parallelize as much in general compared to SDIR and Pluto. Looking at the preliminary results for the sequential benchmarks, we noticed that SDIR is generally on par with all the other compilers. In the parallel benchmark, we noticed that Poly doesn't parallelize too much, and unexpectedly, it seems to perform worse in the sequential benchmark. In the plot for the GenVer benchmark, we noticed that SDIR and Pluto are much faster than the parallel version. This is because the problem size is not large enough to profit from the parallel execution. However, DaCe has checks for small map scopes and executes them sequentially if they are small enough. We can see this if we go back to the parallel benchmark. As you can see, SDIR is approximately twice as fast compared to Pluto on the GenVer benchmark, because it noticed that the problem size is small and didn't parallelize as much, which means that there is less overhead, and of course, it's not perfect. SDIR still performs worse than the sequential version. Nonetheless, these results show that languages compiling to the Arithmetic, MemRef, and SCF dialect could increase their performance for single and multi-core machines by utilizing the SDIR dialect and optimizing with DaCe. To summarize, in this presentation, we showed why we want to create a data-centric dialect, then looked at the design of SDIR, and showed how we convert to SDIR and translate to SDFG. Lastly, we showed that languages compiling to the Arithmetic and MemRef and SCF dialect can potentially increase the performance by converting to SDIR. Thank you for your attention, and we are available for your questions now.
Thanks a lot for the presentation. And yeah, let's move on to questions. We only have 10 minutes left.
Hi, I have a question. I'm too lazy to write it in the chat. So you tried on Polybench Large, and as far as I know, Polybench Large fits into L3 cache on modern machines. Did you try extra large, or like especially the thing that is targeted at memory motion? That would be important.
No, we have not. Although it is covered in my thesis, but the evaluation in my thesis was far more specific than this one. So
cool. So please link it in the chat. I'm interested to see.
I think it's also linked in the forum.
Okay.
So
it's in the announcements on Discord. Yeah.
Yeah.
You don't have to be lazy to unmute yourself. Questions are not intended to be asked in the chat, so feel free, anyone, to unmute yourself like Alex and asking.
If I could raise some, is there a question? So if I could raise some point for discussion, I think one of the pain points that we had when we were developing, the converter and the dialect is that, the question marks and the symbolic sizes that I think we also have some discussion here in the chat. And I'm thinking that for symbolic expressions, some of the infrastructure already exists to some extent within MLIR, in the sense that you can have affine expressions, right? So maybe something could be added to the syntax to allow, like we were thinking, maybe to add like dollar and then some the same syntax of the affine or affine expressions as symbolic expressions, and then we could use that to understand sizes better. So what do you think?
So I answered to that in the chat, so I can answer again, I guess. This has been discussed, I don't even know how many times, like really many, many times. And there is a reasonably simple thing that can be done, and there are more complicated things. So reasonably simple thing keeps types isolated from everything else. So you can say within one type, you might relate different dimensions or different elements of the type. So you can say a second dimension of a tensor is twice as big as the first dimension, or the last dimension is divisible by 5, or something like that. But it will be local to a type, and that it just requires you to define a new type and possibly adapt operations to work with that type. And then there is a full spectrum of something that becomes more of a dependent type, where you have a type that depends on an SSA value. And that I tried several things. I think Jacques tried more things. I know Nicholas tried more things. And I personally have not convinced myself that it can be done without having dependent types as a first-class thing in MLIR. I'm not saying it cannot be done. I just haven't found the way.
So I think there's something simpler than that, Alex, which would be to allow to have types not dependent on SSA values, but only dependent on attributes. And then it sort of becomes a syntactic thing of how do you write these things easily? And you'd sort of have an expression of attributes that is different from an expression of SSA values. And they're really sort of two separate languages. And that's nice because it ensures that you can always have type convergence and do type checking on the rest of the SSA IR.
Yeah, so one thing that I don't fully understand is what do you mean dependent on attributes, because we can already have types that have attributes as parameters.
Yeah, so I think then it comes down to how do you spell them in the IR, and what is the infrastructure that we have to support it, right? So today the memref type doesn't do that, right?
Well, it kind of does, because, well, you can abuse this layout attribute that is there, and it's just an attribute. So if you wanted, you could put literally any, well, not any attribute, you need to implement an interface for that. But as long as you do that, you can attach any other information to that attribute and put it into memref.
Right. So okay. So there's one additional thing that you need, right? Which is the ability to reference I think something like a type alias.
Yeah.
Which is, and then the type alias sort of serves as a placeholder for the parameter. So you can keep the information around that these two types have the same size.
Yes, that's exactly, I think the problem is we want, like, I see how to do it locally for a type, and I see how to relate it with SSA values. And what you suggest is probably what we actually need is a relation between types or elements of the types. And then, well, one way to do is both types. Like you have I can see a slightly awkward recursive structure where you have an attribute that refers to both types that themselves refer to an attribute. And this way you can find the types you're related to. It's easier to write than to say.
Yeah. So I basically, we kind of did something very similar to this in a different system outside of MLIR, right? And this sort of keeping them separate means that you don't end up in a full dependent type system, which I don't necessarily think is a good idea, right?
Yeah,
so
I agree with that.
Keeping it slightly simpler, but allowing you to express things like a parameterized type that is some value that I don't know, but I can still sort of locally type check things is useful and interesting, I think, and maybe would solve a lot of what Tal was looking for.
And perhaps an interesting one here would be like, I think, as Alex mentions, like, I have a random prototype. Alex has had a couple of random prototypes. Perhaps we should actually just have a prototype show and tell with like different limitations of the different things, and discuss. I mean, I think it is like, I will say, like, the dependent types here also is, I think there's quite some spectrum. So the one I have is very much on the shallow end of it. Like no affine, no trying to have even arbitrary expressions or anything. Like equality is where I stop. But yeah, I think it was actually interesting to see. I mean, I think for me the thing I haven't quite. I mean, I can understand the value of the dependent type, sort of like at the front end, the verification, all of that. I'm curious what happens like at the step below that. Meaning, like it seems at some point, we have to get we would drop that information. Like as we go lower in the stack, at some point we would not care. And it's sort of like interesting. Like, what is that section where, what you can take advantage of it? Does it, is it more on the language side because it's a user thing? Is it more on the coding side? Like I think that's a lot of, like the utility. What all we want to do with it is sometimes, it's something I'm not exactly sure what the answer is.
If I may give an example, so we have a lot of data-centric transformations that depend on these what we call symbolic expressions, right? But in that sense, let's take, for example, vectorization. So it's not necessarily the shape, but the layout that could determine whether you need extra operations, like if something would be unaligned at a certain level, and this is a bit lower than the front-end level. And we have a lot of checks that we do, especially when we talk about fusion, for example, where we check for overlapping, so whether the two segments are intersecting with each other. And then when it's symbolic, it's very helpful for us.
And it also feels like it's a reasonably small and well-defined subset of what dependent types could be. So to echo Jack's explanation, is I would see that if you're writing a front-end language, you probably want as much expressivity in your dependent types as possible, but the lower you go, the more constrained it gets. So like at LLVM, you want to drop everything. At CodeGen style transformations, you want that kind of information, but you don't want the like full-blown functional theory behind it. And generally in a like mid-end of the compiler, I wouldn't want to need to understand functional type theory. Because like I lose 70% of people who can contribute.
Yeah, and I think there, that trade-off of how do you keep it simple and usable and efficient is an important trade-off when you start making things more complex and expressive, right? And to some extent, you probably can't get both you can't make it really simple and also really expressive at the same time, right? So there has to be some trade-off there.
Actually, again, I think that one thing that you could do is it's not necessarily some type dependency graph. It would be like a tree with 3 levels, right? The first level, at least that's how we constructed it. Again, we could be wrong here. The first level would be a named set of unique symbols, right? The second level would be expressions that are defined on top of these symbols. And the third one is a memref, right? That memref could have hashtag something, and that would go to the one level above, and that could only use some of those defined named symbols, I think. We never needed more than that.
Yeah, so one specific problem for you to think about with defined things is memref can be in a function signature, and function can be referenced from external modules, which would need access to those symbols you define, but would not have it. So I think it can be worked around, just that we thought about something similar. But I guess the other approach is, or in addition to show and tell of prototypes, we can try to think of what we need, and based on those needs, maybe there's just some small thing we can do and put a new type or evolve memref. And if you can, like, if somebody could go to the forum and just list, we need 1, 2, 3 these things as a response to a DM announcement or something, or as a new topic, we might be able to make progress on that. It'd be nice.
All right, and I think we're out of time, but thank you for the lively discussion. And thanks again, Berke and Tao, for the presentation. I'll publish the video and the slides online as soon as possible. See you next time.